Decoded.
All right, everybody, welcome back to Book Decoded. I am pumped for this one.
Yeah.
Today we are diving into Carl Zimmer's Airborne. And let me tell you, it is going to blow your mind.
Absolutely.
So we're going to be talking about all the invisible stuff.
He's got this incredible way of connecting these seemingly random things.
Right.
And what comes out of it is this fascinating picture of how life and even like ideas travel on the air.
Okay, let's jump in.
Let's do it. Let's start with an event that Zimmer really brings to life, the Skagit Valley Corral.
Oh, yeah.
Do you remember this?
I do.
Back in early 2020, really kind of drove home how sneaky this whole airborne virus thing could be.
It's just terrifying this choir in Washington State, right?
Right.
They had just one rehearsal.
Just one.
And 58 members got COVID-19.
It spread like wildfire.
3 of them ended up in the hospital and 2 people died. It was awful.
Awful. And what it showed us was that even something as simple as singing,
Yeah.
releases these tiny droplets, microscopic droplets.
Huh?
Not the big ones you see when someone coughs. These are way smaller.
Oh,
They float around longer, they go further.
that's scary.
Really changed the game.
It did. It
Yeah.
really challenged everything we thought we knew at the time.
Mm-hmm.
I remember those early days. It was all about washing your hands, wiping down surfaces.
Right, like we were dealing with the flu.
Exactly. And even within the choir itself. Some people were masking up, others weren't.
Sure.
Nobody really knew what to do.
It was a confusing time.
So the Skagit Valley thing wasn't just an outbreak. It was like a wake-up call. It forced us to re-examine how we think about these invisible threats in the air.
Absolutely. And that takes us way back in history.
Oh, yeah.
Zimmer talks about these early explanations for disease.
Okay.
Like the concept of miasmas, this idea that like bad air, foul poisonous air
Right, yeah.
was what caused plagues and all these big outbreaks.
Galen and those early Arab doctors.
Exactly. They were trying to make sense of these devastating events.
Like imagine the plague hitting Syria back in 1258.
Oh, yeah.
Some folks actually believed that the stench from the sacked city of Baghdad, hundreds of miles away, had corrupted the air.
Wow.
That's how they thought disease traveled.
That was their understanding.
Okay, so then we come to the 1500s.
All right.
We've got Girolamo Fracastoro and his idea of seeds of disease,
Right.
these tiny unseen particles that made people sick.
Yeah.
But, as Zimmer points out, Fracastoro was more of a thinker than an experimenter.
Interesting.
So, like, his explanation for syphilis
Yeah.
involved these, like, sharp seeds burrowing into people. I know, right?
It's a little rough.
So without the ability to see these tiny things, it was a lot of guesswork back then. Enter Antony van Leeuwenhoek and his amazing microscope in the 1600s.
Oh, yeah. Game changer.
He starts looking at these teeny tiny living things in water, even scraping them off his own teeth. But what this did was bring back the idea that living organisms were behind contagious diseases.
It wasn't just bad air anymore. It was something you could actually see, even if it was super small.
Right. It wasn't just this mysterious miasma.
Exactly. So by the 18th century, the idea that microorganisms were causing things like plague and tuberculosis, it was starting to gain some traction.
But not everyone was on board, right?
Not all.
Like in the 1800s, there were still some serious skeptics.
Oh, yeah. People like McLean, he just scoffed at the idea of germs having this unknown and incomprehensible power.
Right. It seemed too far-fetched.
Way too small to cause so much trouble.
Okay, but the investigation into what was actually in the air was heating up.
It was.
Zimmer tells the story of Christian Ehrenberg,
Okay.
who found airborne microorganisms,
Right.
including these silica-shelled creatures that looked exactly like freshwater species from South America.
No way.
But they were in dust samples sent to Darwin.
Whoa, how did freshwater creatures end up in the air traveling across continents?
Right.
That's amazing.
That's the aerobiome for you.
It really is this vast, interconnected web of life.
And then, boom, the European potato blight hits.
Oh, yeah.
This plant disease just went crazy.
Devastated.
And it got the contagionists thinking hard about the air.
They realized the fungus causing the blight, these spores could be carried by the wind.
And Berkeley's observations were crucial here.
Yeah.
He noticed that these spores could travel thousands of miles on trade winds,
Wow.
literally hitching a ride across continents.
The air is a highway.
But it's a global transport
Kind
system.
of better or worse.
And then, of course, we have the one and only Louis Pasteur.
The legend.
His work on fermentation was game-changing. He figured out that yeast was in good juice.
Oh, okay.
But in spoiled juice, there were these lactic yeasts, which we now know are bacteria.
Right.
And what made Pasteur so convincing was his experiments.
He was meticulous.
You know that famous swan-necked flask experiment?
Yeah.
It proved that new life didn't just magically appear. It came from existing microbes in the air.
Busted the myth of spontaneous generation wide open.
It was a mic drop moment.
It really was.
And then Zimmer talks about Pasteur's germ-collecting forays, where he actually set out to capture these invisible critters from the air.
He was a pioneer.
Others had found them in different places, but Pasteur was the first to systematically collect what was floating around us.
Giving us a glimpse into this hidden world.
It's amazing. But even with all this evidence for germ theory, the sanitarium movement was still really popular, wasn't it?
Oh, yeah. They were all about cleaning up the air through ventilation and better building design.
The New York City Board of Health even made it mandatory to have thousands of windows in dark interior rooms. They wanted to let the light in.
And the fresh air.
Exactly.
That makes sense.
And Maxim Pettenkofer became like the poster child for this movement.
He was a sanitation rock star.
The drop in typhoid fever in Munich after they followed his advice was huge. They even built him his own institute.
That's impressive.
But here's the thing. Pettenkofer was still a hardcore believer in the miasma theory when it came to cholera. Even his germ theory was gaining ground. He thought cholera was caused by these miasmas rising from the soil.
Interesting.
Which went against what John Snow had discovered about contaminated water. So when Robert Koch found the Common bacillus in cholera patients,
Big discovery.
Pettenkofer tried to make it fit his miasma theory.
How'd he do that?
He drank a whole culture of Common bacilli to prove his point.
He what?
Yeah, it's wild. He had some mild symptoms but didn't get full-blown cholera.
Talk about dedication to your theory.
It shows how hard it can be to change people's minds, even with new evidence.
Absolutely. So the debate raged on, but the focus shifted more to droplets versus dust.
Right.
Zimmer talks about Carl Fluge's work on tuberculosis.
Okay.
At first, he thought dust was the main culprit.
Makes sense.
But then he did these experiments where volunteers would cough and sneeze harmless bacteria
Oh, wow.
after rinsing their mouths with it.
So he could see where the microbes went.
Exactly. It really started to point towards these exhaled particles.
Interesting.
And that led to Johannes Mikulicz inventing the gauze mouth bandage, the OG face mask.
Oh, wow.
Fluge's tests showed that even 2 layers of gauze could block these bacteria.
That's pretty cool.
Early recognition of the power of simple barriers.
But then we have Charles Chapin, a huge germ theory guy.
Okay.
But he was skeptical about long-distance airborne transmission.
How so?
He thought our breath was totally free of disease germs,
Oh,
and that the droplets from coughs and sneezes only traveled a short distance.
interesting.
His view really influenced public health thinking for a while.
So we went from miasma to droplets.
But those smaller, longer floating particles were still kind of overlooked. And the curiosity about what was in the air wasn't limited to ground level.
Right.
Zimmer talks about Albert Miquel's measurements in Paris.
Okay.
He tracked the daily and seasonal changes in the types and amounts of airborne spores.
Like taking a census of the invisible world.
Exactly.
Very cool.
And then there's this crazy story of Hector Christiani.
What happened?
He basically hitched a ride with a famous balloonist
No way.
and took these early aeroscopes with him to try and collect microbes almost 2 miles up.
Wow, that's dedication.
He was a pioneer exploring the unknown upper atmosphere.
That's amazing.
Zimmer even mentions Otto Lilienthal's glider flights as another way humans were taken to the skies.
Right, the early days of aviation.
And it's kind of bittersweet because he took these groundbreaking photographs from up high, but then he tragically died in a crash.
It's a reminder of the risks people took to learn about the air.
Absolutely. So then this curiosity extended to threats in the air, especially to agriculture. Elvin Stakman's research on wheat rust showed how wind-borne fungal spores could travel incredibly far.
Interesting.
The government even started linking the fungus to wartime enemies.
Wow, so they were thinking about airborne threats beyond just human disease.
Yeah, it became an economic and political issue too.
Makes sense.
And then you have Charles Lindbergh, the famous aviator.
Right.
He was also a science enthusiast and teamed up with Fred Meyer to collect microorganisms in the upper atmosphere during his flights.
That's cool.
Initially, they were focused on how plant diseases might spread,
Okay.
but this understanding of airborne organisms took a dark turn as well. Zimmer talks about the military's interest in biological warfare during World War I.
Not surprising.
There were even suspicions about German bombs carrying deadly germs.
So the idea of using airborne pathogens as weapons was already there.
Yeah, and by the 1930s, the American military was imagining these catastrophic airborne biological attacks.
Scary stuff.
Stegman even suggested these shotgun attacks using mixtures of pathogens to destroy crops, a dark side of aerobiology that was kept secret.
It's a reminder that scientific knowledge can be used for good or evil.
So then we come to William Firth Wells and his groundbreaking work on airborne infection theory.
All right.
He developed the air centrifuge to collect airborne bacteria, but he faced pushback at Harvard.
People weren't ready for his ideas.
Not quite.
It's always tough to change the status quo.
Wells was a key figure in shifting our understanding of how these infections really work.
His air centrifuge allowed for a much more precise way to study these tiny particles that hang in the air.
And he did this really cool experiment using sneezing powder in his hygiene class.
Okay, what did he do?
It showed how these little droplet nuclei could travel far and spread infection.
Smart.
And his experiments with influenza viruses were even more convincing.
What did they show?
They showed that these viruses could stay in the air for like half an hour and still be infectious.
Whoa, that's a long time.
It meant that just focusing on the big visible droplets wasn't enough.
We had to start thinking about those tiny droplet nuclei.
Exactly, and the New York Times even recognized Wells's work early on.
They called him and Fred Meyer the guys who were figuring out this living atmosphere.
So the idea was out there.
But it still needed more evidence and wider acceptance.
Right. The Wellses even experimented with UV lights in classrooms to kill airborne germs.
Did it work?
They saw a big drop in measles cases.
That's awesome.
But it's important to note that Mildred Wells played a crucial role in this research.
Well, of course.
And she even published her own work independently.
Good for her.
But it eventually led to her leaving the laboratories for the study of airborne infection.
Sounds like there might have been some tension there.
Possibly.
It's sad when people's contributions aren't fully recognized.
It is, and then wartime research really pushed things forward.
In a way, war can be a catalyst for scientific progress.
Ira Baldwin was studying flu transmission in army camps, and masks were being used to control outbreaks like the Noonic Plague in Manchuria.
They were starting to understand the importance of protecting soldiers from these airborne threats.
And William Wells got involved in wartime research, too.
Where did he go?
He went to Edgewood Arsenal and used his infection machine to show how diseases could spread through the air to animals.
Wow.
It was more proof that airborne infection was a real thing.
So his work was starting to get more recognition.
It was Roderick Heffron, who was an expert on pneumonia, called Wells's work Clear Proof of Airborne Infection.
That's a big endorsement.
It is, and it led to Wells collaborating with Max Lurie on airborne transmission of tuberculosis in rabbits.
Interesting choice using rabbits.
They were trying to figure out how this major public health threat was spreading.
It was important work.
But the science wasn't always straightforward. Those UV light experiments in schools that showed such promising results with measles,
Yeah.
they got some headlines.
Sure.
But then later trials with soldiers had mixed results.
So the initial excitement was tempered a bit.
It was.
It shows that even when things seem promising, more research is always needed.
Absolutely, and sadly, despite all his groundbreaking work, Wells eventually lost funding from the Commonwealth Fund.
Oh, no, why?
It seems like his personality played a part.
That's unfortunate.
It happens sometimes. Even brilliant scientists can have their struggles.
It's a reminder that science is a human endeavor with all its complexities.
So then in the post-war era, we have Theodore Rosebury working at Camp Detrick on biological weapons,
Oh, wow.
including anthrax bombs.
That's intense.
It's a dark reminder of how scientific knowledge can be misused.
Absolutely a sobering thought.
Rosebury himself had some internal conflict about it and eventually pushed to publish his research on airborne infection.
Even though the government wasn't thrilled about it,
He felt it was important to get the information out there.
he even received the Decoration for Exceptional Civilian Service.
Wow.
So his work was recognized for its importance despite the controversy.
And then there was Irving Langmuir.
What did he do?
After the war, he started warning about potential airborne biological attacks. He used these really striking visuals, like Jennison's high-speed photos of sneezes,
Wow.
and even a wearing blender demonstration to show how easy it was to create germ-filled mists.
Talk about a wake-up call.
It reflected the anxieties of the Cold War and this new kind of threat.
Yeah, the fear of the unknown.
And Zimmer even mentions this secret army experiment where they sprayed Serratia marcescens, supposedly harmless bacterium, in the U.S.
What? Why would they do that?
They were trying to study how airborne particles spread, but it raises some serious ethical questions.
It does, especially about the potential for unintended harm.
Right. So fast forward to the 21st century, and we have the SARS outbreak in 2002, 2003, and Hugo Lee's investigations into the Amoy Gardens and Prince of Wales hospital outbreaks suggested that the virus was spreading through the air beyond close contact.
Interesting. So airborne transmission was back on the radar.
It was, and Lydia Maraska was a huge advocate for revisiting William Well's work on droplet nuclei.
It's amazing how sometimes we have to rediscover old knowledge. She pointed out that there hadn't been much research on the physics of how these droplets actually behave.
It's crazy to think that something so fundamental was still not fully understood.
But that's often the case in science. There's always more to learn.
So when COVID-19 hit, the WHO initially downplayed airborne transmission.
They were still focused on the larger droplet model.
But scientists like Jose Luis Jimenez and Shelley Miller started raising concerns based on their expertise in aerosol science and indoor air.
They knew that the air we breathe indoors especially can be a major factor in how viruses spread.
And as we all know, our understanding of COVID-19 transmission evolved during the pandemic.
It was a learning process in real time.
Definitely driven by events like the Skagit Valley Corral and the work of scientists who were pushing for recognition of airborne spread.
Right, it was a real paradigm shift.
Groups like Group 36 and Lydia Maraska, who wrote that open letter about airborne transmission of SARS-CoV-2, really had to fight to be heard.
It shows that even in a crisis, it can be hard to change established thinking.
And we saw these simple solutions like Corsi Rosenthal boxes popping up in schools.
People were taking matters into their own hands.
And new variants like Alpha and Delta just reinforced the importance of airborne transmission.
Donald Milton's research showed that these variants could produce way more virus in exhaled breath.
It was like the virus was adapting to spread more effectively through the air.
That's unsettling, but also fascinating.
And in the end, as Zimmer points out, there's been a slow but definite shift towards accepting that airborne transmission is a key factor in lots of respiratory diseases.
Hugo Lee even argues that all respiratory viruses are at least partially airborne.
It's a huge change in perspective.
It really is a culmination of decades of research.
So it's been quite a journey learning about how our understanding of the air has changed over time.
From those early ideas about bad air to the complexities of droplet nuclei and this vast aerobiome.
It's amazing how something we take for granted, like the air we breathe, has such a profound impact on our lives.
And how our knowledge of it continues to evolve.
The big takeaway is that the air isn't just empty space.
It's teeming with life, both helpful and harmful.
And understanding how things move through the air is crucial for our health and how we live.
Absolutely. We need to be more aware of this invisible world all around us.
It's not just about avoiding coughs anymore. It's about understanding how these tiny particles can travel and potentially infect us.
And this knowledge will likely change how we design buildings, how we think about public health.
It makes you wonder what the future holds, what kind of changes we'll see.
Will we start designing buildings with better ventilation systems?
Will masks become more commonplace even outside of pandemics?
Will we invest more in air filtration technology?
It's exciting to think about the possibility.
It is, and it all stems from this deeper understanding of the air we breathe.
Thanks for joining us on this incredible journey through Airborne.
It's been a pleasure exploring these ideas with you.
And for all of you listening, keep those questions coming.
We love hearing from you.
Until next time, stay curious.
And maybe get yourself a good air purifier.
You never know what's floating around out there.
You really don't.
Thanks again, everyone. See ya.